All right, so a lot of you guys might feel like you've done a million of these problems before. It looks really familiar. You know, you have two blocks on a slope and they're sliding, friction, no friction. What's the acceleration for the two blocks? But in this case, we have a pulley that actually has mass. So for every other previous problem that we've done for the dynamics, we've neglected the mass of the pulley, even though it does exist. But in this case, we are not neglecting the mass of the pulley. We're actually including it in the system. What that means is that there's going to be some kind of torque on this pulley. And so when we're doing our sum of forces equations for the system, in order to like relate these two tensions that are not necessarily equal here, of this sum, right, like T1, I'll just say maybe coming out of the pulley here. So I have like some T1 out of the pulley, T1 and then some T2. In order to relate those, we're going to need to look at a sum of torques equation for this middle pulley here. Okay, so let's start with a few things that we know about this problem. We're told by the problem that we have kinetic friction on the wedge surface. You can pause and read the problem statement right now. I'll try not to read the entire thing out to you just for the sake of time. But we do have some friction, right, acting on both of these surfaces. The same on both of these surfaces, and it's a kinetic friction force that's preventing these blocks from sliding. But because we do have some motion, these blocks are accelerating. This M2 is pulling this M1 forward. What we're going to do is we are going to model the system and then try to figure out the acceleration of the two blocks by using this relationship of the pulley and the two tensions and the torque equation. Okay, one thing too that we know about this system, we have rolling motion here with this pulley. So we've talked about this a little bit in previous problems, but basically what we're saying is that the tangent acceleration, in this case, because the wire is going over the pulley, as this pulley is rotating, the acceleration that we're going to see is the tangent acceleration, right, over the top, that tangent acceleration coming off the pulley. And that tangent acceleration has a relationship with r theta, so long as that string is not slipping, right, and not affecting that acceleration from the rolling motion, okay? So we also know that we have a pulley that is a disk. So this is the mass moment of inertia for a disk that is spinning about the center. And then this is just our general torque equation that we're going to end up using later. Okay, so our approach for this problem is always 1, free body diagram, okay, 2, sum of forces, sum of torques, 3, what else? Like what other equations do we have? What else can we use to solve? And in this case, I think it would be our equations, 1 and 2 here. And then 4, algebra. So this is going to be a really long problem. I may break it up into 2 parts, and the second portion of this posting may just be the algebra. Okay, so 1, free body diagram. So I kind of pre-put together this from the solution guide for this guy because I think it's a lot more readable. So this first one is M1, this first block. We have the kinetic friction, right, going backwards. We have the tension. We have the mass 1 times gravity, right, and then we have the normal force on its surface, okay? Then for the second block, we have the normal force on its surface, right? We have the weight, and this is just kind of showing how the weight x and y components would be broken up, right? This would be like Wx, Wy. And then last, we have the pulley over here. We are kind of neglecting this normal force and this like mg force of the pulley and treating them like internal forces in this particular problem because they're not really going to factor into what we need. And we're really only going to look at a sum of torque equation for the center part, okay? Okay, so one odd choice in this problem that you're allowed to do is for each mass, you can give it a different coordinate system when you're trying to solve for things in the system. So we're going to use an xy coordinate system, an xy coordinate system for this first block, okay? And then we're going to use a tilted xy coordinate system for the slope. And that's perfectly fine, okay? In the end, what we're going to do is we're going to have an equation where we're going to relate this T1 and T2. And we really only care about how these, like the relationship of these forces between each other. I don't know if that's explaining it very well, but this is allowed. We can do this and it's going to be fine, and I'll show you and it will work out just fine. Okay, so let's do all of our sum of forces here. The sum of forces in the x direction, okay? for this we have T1, because this is in our positive x, right, minus FK1. And that's going to be equal to the mass times some acceleration, right? And the mass in this case is m1, so let's be careful with our subscripts, m1a. Okay, the reason why we have some acceleration, right, is because this block is being pulled along here, right, and this block is slipping down, so they're both accelerating, okay? All right, so now we have, let's see, sum of forces in the y. We have n1 minus m1g, okay, and that's going to be equal to 0 because we have no y acceleration. It's just sliding along this surface. Okay, now let's look at this guy. So sum of forces in the x, sum of forces in the y. So we tilted our axis for this, right, to make our math easier. Okay, and so our wx is what's going to be in this positive x direction. So wx is going to, let's put it in right away, I guess. So it's going to be, wx is going to be w sine of this theta angle is going to equal wx, and then w cosine of this theta angle is going to equal wy, because wx would be right across from the angle, and wy is adjacent to the angle, okay? So sum of forces in the x direction, so our w is equals m2g, right, which is what we see here. So we have, what is our wx? m2g sine of theta, right, for wx, minus t2 minus fk2. Okay, did we get everything here? So did we get everything along the x? Yes, just those three forces. Okay, let's look at y. Okay, what is along the y here? So we just have the two forces along the y. We have this n2 and then this wy. Okay, so we have n2 as our positive force minus, and our wy is equal to, we found w cosine of theta, so that's m2g cosine of theta, right? Cosine of theta. Okay, so, all right, what is our forces in the y equal to? Well, that's going to be 0 because we have forces equal to mass times acceleration. We don't have any acceleration in the y. What about the x? Okay, so in the x direction, this block is sliding down this way, right? So we are going to have some acceleration. So it's going to be equal to m2a, okay? And we know that that acceleration, okay, is going to be shared between these two blocks, right? This acceleration and this acceleration. So the shared string here. All right, what about our pulley over here? What's going on here? Okay, let's kind of look at what's going on with our radiuses. Oh, I thought that was my dotted one. There we go. Okay, so notice that these are both an r distance away, right? And they're at a right angle. And so we notice that they're just basically pulling in two different torque directions. So if I sum up my sum of torques, right? Torque, the general equation is equal to r times the f times sine of theta. We notice that the angle for both of these is equal to 90 degrees, right? And then the length of the r value from the rotating point is going to just be this big R, right? So let's do them both separately and kind of look at the sign convention. So we know that for a torque, if we rotate clockwise, okay, then that is a negative torque, and then if we rotate counterclockwise, that is a positive torque, okay? So in this case, if we look at, that's going to be, clockwise rotation is going to be T2, right, because that's going to cause it to move clockwise, and then counterclockwise rotation is going to be T1 over here, okay? All right, so sum of torques here, we are going to have R, right, T1 or sine of 90 degrees, okay, and RT1 sine of 90 degrees is the positive counterclockwise. I'm going to have minus RT2 sine of 90 degrees, okay, and that's going to be equal to, sum of torques is going to be equal to this I alpha, right? Okay, so wow, we got a lot of stuff going on here. This is a very long problem. Okay, so we have our sum of torques equations here. Okay, we have our sum of forces equations. Okay, and then we have the sum of forces equations. Okay, so what are we trying to find? We were trying to find this A value here. So let's try to isolate a little bit of let's see, let's think about this. So we don't know T1 or T2, right? We don't know these, but we do have a relationship with this torque equation. So we're going to start out by simplifying this torque equation, okay? So I'm going to start over there. So I have, from my torque equation, I'm going to call that 1 for that block. I'm going to call these 2. Actually, I'll just label them based on the masses, right? So this was like mass 1, mass 2, and then we'll call this like 3. So we're going to start at 3, basically. Okay, so let's see what we can simplify here. So I had my sum of torques, right, was equal to R, right, times T1. Okay, I know sine of 90 degrees is equal to 1, so I'm just going to kind of simplify these right away. So I have T1 minus T2, right, is equal to I alpha. So what I did was I know they're both multiplied by R, sine of theta, or sine of 90 degrees is equal to 1, and then I just sort of factored out this R to get this right here, okay? So it's going to be equal to my I alpha. Okay, and because we want our net alpha for this T1 minus T2 equation, like we want our alpha to be this way, right? Our angular acceleration should be this way. That's going to also be negative because angular acceleration and torque follow the same sign convention. Because this is clockwise, we're going to look at a negative angular acceleration for this. Okay, so we're going to have I negative alpha. Okay, and so we're going to plug in alpha is equal to A over R, okay? And so keeping that negative, because we know that this A, so this A tangent, right, is going to be equal to the acceleration that we're trying to find, right? So we know that this tangent acceleration, like coming off of this wheel, is going to be equal to the acceleration of the string as it moves across, and therefore the acceleration of these two blocks. So we know the system is connected in that way, and so we can use this rolling motion with no slip equation here. Okay, so that's going to allow us to sub things out. So we have R times T1 minus T2, and I'm also going to plug in our mass moment of inertia equation that we were given at the beginning, right? This is just mass moment of inertia for a disk. And then we have a negative A, we're going to just model our AT as A because they have a shared acceleration. So we know it's that same acceleration across both of them. Okay. And then if we solve for this and simplify, we are going to be able to have R times T1 minus T2 equals 1/2 mR times A. So this is a negative, so it's going to turn into R times T2 minus T1, right? No, wait, I'll just leave the negative on the other side. I think that I might be trying to make something more confusing than it needs to be. Okay, and then we can also cancel out the r's on both of these sides here. Okay, so far so good. Okay, so now we have an expression, t1 minus t2, right, is equal to negative 1/2 m. Okay, oh, times a. Okay, so this a is what we want to find. So we have two expressions that have t1 and t2. So we can rearrange them essentially to get an expression for T1 and an expression for T2 and just basically do T1 minus T2 and then divide it by 1/2 m, negative 1/2 m, and then we can get our expression that we're looking for here. So let's go ahead and do that. Quick before I do that T1 and T2 equals, let's also do this, what we talked about part 4, right, where we're just like everything else. Let's just figure out our FK1 and FK2 expressions. FK1, FK2. Okay, so that's equal to mu k, right, times n1, mu k times n2. You need the normal force on the surface that the friction is acting on, okay? So mu k, and then what is our n1 here? From this expression for the f of y, we can get n1 is equal to m1g, and then from this guy, we can get n2 is equal to m2g cosine of theta. So let's just use both of those right away. Mu k, and then n1 is m1g, and n2 is equal to m2g cosine of theta. Okay, so we've also got our frictional equations here. Okay, so now that we have those, Let's rewrite these guys. So what we're doing right now is we're rewriting these equations, this f of x, right? And then this f of x in terms of t1 and t2. Okay, so we have, um, we have t1 is going to be equal to m1a, okay, plus mu k times, or m1g, okay. And then T2 is going to be equal to negative M2A, okay, plus M2G sine theta minus mu K, M2G cosine of theta. So being systematic about this really helps. Okay, so, all right, so we have this equation, right? We have our acceleration here, and then we have these equations for T1 and T2. So we're going to take equation 1 and we're going to sub in number 2. Okay, so we have T1 minus T2, right, equals negative 1/2 MA, right? And then we're going to plug these guys in. So we have, right, T1 blank, okay, minus this T2 minus this guy. And let's distribute our negative right away. 1/2 MA. Okay, and so let's go ahead and do, I'm going to make this positive, positive, negative, because it's less things to distribute a negative for. Negative M1A minus mu K M1G, and then all the rest of this, right? Just for the sake of not writing everything out again, is equal to 1/2 MA. Okay, so what we need to do now is group all of our A terms so we can get everything together. Okay, so we have, where are our A terms? So we have an A term here, right? We have an A term here, so let's move them to the right side and then rewrite everything else. So let's go ahead and copy so all of these guys, right, will still be there. Okay, so we have all of this, right? And these were added. And then it's going to be equal to 1/2 MA plus M2A plus M1A, right? So let's group, so 1/2 M plus M1 plus M2, right, multiplied by A, okay, is equal to everything else on this side. Let's see if we can group anything a little bit on this side. So we have a negative mu K, 1, also everything's multiplied by G, so let's pull out the G too. So we have G, right, times negative mu K times M1 plus M2 cosine of theta, and then plus M2 sine of theta, all this times G. So you don't have to do this part, this is just kind of clean it up a little bit, okay? So then we have this expression, right? Okay, and we're just going to divide it by this expression, oops, right, to get A. So divided by this equals our A. Okay, so this is the shared acceleration for, this is just something else. This is the shared acceleration for both of these blocks, okay? So to recap, what we did, and let me just double check to make sure I don't have any negatives off here. So M2 sine, yep, and we're good. Okay, so to recap what we did here, because we had a pulley with mass, we had to use the torque of that pulley to relate the equations for these two objects, okay? We used this torque equation for the pulley in the middle to unify both of these. Some supplementary equations we used were the fact that we knew that this tangent acceleration of the string going over the edge of the pulley was equal to r alpha, and then this tangent acceleration of the string going over the pulley was also equal to the acceleration that these two blocks were experiencing, and so that's what we were solving for. Okay, then basically, so we did all of our sum of forces, everything. We started by simplifying the pulley equation, right? Equation number 3 for the pulley. We started by simplifying that one. And then we took equations from the rest of these guys. We needed everything in y to get the frictional forces because we needed those normal forces. And then we used the x equation. So this was using the sum of forces in the y equations. And then we use the x equations, the sum of forces in the x equations for both of them to get these. Then we subbed in T1 and T2 into this, into our torque equation. We did a lot of simplification and we got a final expression for acceleration.